So this is going to be 115C. Sorry about the cutout. I was talking about Min, the chaos theorist, and according to Min's view, the probability of understanding your karma will vary with the nature of your karma. It will be harder or easier to change your behavior depending on that behavior itself. In chaotic systems like samsara, order can often be introduced through feedback. Min explains how it works. Imagine you are in a helicopter over the Mojave Desert, watching a jeep moving on the rough dirt road on barren plateau. The jeep is veering very sharply to one side, then another, slowing down almost to a complete stop and then speeding up past 90. At times, the wheels creep dangerously close to a sharp gully. From a helicopter, we assume that there are problems with the terrain, that there must be rocks and holes in the roads we simply cannot see from far above. This is how conventional science still operates, assuming that if you could only get a closer look, we would see all the causes. But chaos theory tells us that the real reason for such erratic driving is that the man found out the night before that his wife is having an affair. He is incredibly angry, slightly hangover, and his mind is full of conflicting, chaotic ideas. So you need to fix his state of mind, not the road. But maybe you don't even need to fix that, because this situation has gotten so chaotic that it's about to get orderly on its own. This is where the notion of feedback comes in. In this situation, the fact that this man keeps almost driving into the gully, the way he almost swerves off the road into those cactuses, will change his mind. The danger he's causing himself will feed back to his anger and subdue it. He will realize that his anger is about to kill him, and he will calm down a little so he doesn't drive off the road, because he doesn't actually want to die over this woman. It changes what I call the parameter space, which is in this case his state of mind. From time to time I talk to Min late at night. He sleeps sitting up in a futon chair in the modern studio apartment in Palo Alto. He hates the dark and he hates to be alone, which is why he lives in apartments where he can hear the presence of others. In the meantime, he's looking for a wife who will be there all the time but not ever really being there. A typical prescription for a man who has, by his own admission, been chasing fluctuation his entire life. But the point is, he imagines his life as continued meditation. I'm meditating all the time, says Min, but I meditate not with quiet, but with more noise. I go to Las Vegas and play the slot machine. That's how I meditate. In the dawn of Tantra, I happen on the following response Trungpa Rinpoche gave to a question about the complexities and confusions in everyday life. Question: the more confusion, the more unity. Trungpa Rinpoche, that's what tantric people say. Question: you mean the more confusion there is, the more difficult it is to stamp a system on reality? Trungpa Rinpoche: chaos has an order by virtue of which it isn't really chaos. But when there is no chaos, no confusion, there is luxury comfort. Comfort and luxury lead you more into samsara, creating more luxurious situations, adds further to your collection of chaos. All the luxurious conditions come back on you and you begin to understand them, which leads you to further understanding that, after all, this discomfort has order in it. Maybe Min had a point in all this disorder. I have never done the kind of meditation you talk of, but I understand it. Truly, I think that the underlying fluctuations of the universe is lurking in meditation. When someone meditates very well, they can sense the underlying fluctuation of the universe, the pulsing of the matter-antimatter that is the nature of things on a subatomic level. Again, I'm reminded of Trungpa Rinpoche, writing about meditation, practicing letting thoughts come, play out their energy and go. Touch has no meaning without go. They are simultaneous. That simultaneity is mindful. Such conceptual unions run throughout Buddhist teaching, as in the simultaneous union of wisdom and compassion that is enlightenment. Jeffrey Hopkins, in his introduction to Kalachakra Tantra, Rite of Initiation, goes so far as to ascribe a charge to the aspect of mind. One is the clear light of mind, a positive phenomenon. The other is the emptiness of inherent existence of the mind, a negative phenomenon. I show Min a painting of the deities Paramasukha and Chakra Sambhara in the Yab-Yum union of male and female position, and he drew for me a strand of alternating electrons. I asked Min if the ability to sense this fluctuation, this pulse beat, could be related to what Buddhists call form and emptiness. Oh yes, he replied. What you call form and emptiness, I call matter and antimatter. The constant switching between matter and antimatter that goes on in the universe is the base of every fluctuation. In this case, matter is form, emptiness is antimatter. Speaking of the level of quantum mechanics, matter is born in the past and dies in the present, while antimatter is born in the future and dies in the present. Pure matter, the union of these two, is photon. When light is emitted, this is the evidence of pure matter. Opponent and asserts no other. How perfect, I thought, these gifts of union, the light of matter or the enlightenment of the mind, light and enlightenment. A few weeks ago, Min came to dinner. Afterwards, he was smoking Marlboros with one hand, drinking good champagne with the other, and I wanted him to talk about emptiness. I mentioned the Prajnaparamita Sutra and said that it was known as the Heart Sutra. He heard it as Heart Suture, which nonetheless got him onto the subject of the heart. Trying to lead him back to the emptiness at hand, I read a few choice lines from the work of the Indian Buddhist philosopher Nagarjuna. Neither perishing nor arising in time. What a Buddhist might call the void. I read a few choice lines of the Indian Buddhist philosopher Nagarjuna. Neither perishing nor arising in time. What the Buddhists might call the void, Min responded, we call the vacuum fluctuation of matter, the constant shifting between matter and antimatter that sets up a pattern of beating in every living cell. I'm working on the heart, so take the heart. There is no time in utero that the heart starts to beat. The cells are beating from the start. As cells multiply into what is to become the circulation system, they take their cues from the rhythm of the mother's heartbeat. So the mother's heart is the signal that tells you the fetal heart how to beat, at what rate, and so on. You could ask yourself then, when did the mother's heart begin to beat? And you come to the same problem. If every cell was beating before it was a heart, how could there be a single moment it became a heart? Neither terminal nor eternal means reaction. The heart is a circulation system. There is no beginning and no end. This is something you are just beginning to understand. The reason artificial hearts have been largely unsuccessful is because the heart has been treated as a pump, as a discrete organ. But in fact, I'm finding that the aorta, which leaves the heart, also acts as a pump. And if you follow that further in biology, you see that the heart is actually all the veins and arteries attached to it. Nothing originates out of randomness. Min, there is no such thing as randomness. So of course this is true. Finally, I asked Min to imagine that instead of lecturing at Stanford University in 1995, that he taught at Nalanda, the great center of Buddhist studies in India during the 8th century. Knowing what he does about physics and chaos, if asked to debate the possibility of things having inherent existence, would he rather argue that things cannot be said to exist, or that they can? I would argue that nothing can be proved to have inherent existence. This is why in 1936, the famous mathematician Kurt Gödel developed the axiom known as Gödel's proof. He proves that there is always a problem, an axiom, an explanation that is true but cannot be solved. Mathematics is made of axioms that we know are true. 1 + 1 is 2, and so on. Gödel added just one more, which is that there is always one more thing that is true that you can't prove. This uncertainty is part of the operative logic of mathematics. It is a self-consistent proof. Others have came from various branches of mathematics and proven the same thing. I advance no thesis, so cannot be faulted. Thus Chandrakirti, for the Prasangiki school of Nagarjuna, seeks to demonstrate that it is useless to assert a theory that would seem to lend credence to the idea that there is a solid ontological basis of logic and language. There is no basis in anything because there is no anything. The logic adopted is one that refutes all claim while failing to assert any others. Nagarjuna sought a supreme poise, a technique of dialectical elimination that addresses only the question posited by the opponent and asserts no other. Gödel's proofs holds for that, for whatever is proven, there is something else that can't be. In both worlds there is always another argument or another equation. The arena cannot be closed. Indeed, rather than closing in on themselves, the possibilities between these two ways of describing the universe open up in a mandala-like combination the longer one considers them. There are descriptions in chaos theory of the sequence that water, for example, goes through on its way to chaotic movement. There are bifurcations, double bifurcations, periods of firing, spontaneous generation of local spatial temporal chaos, broken by periods of calm. All these varieties of change are not caused by any outside disturbance, but are inherent in the material itself. I wonder if this could be analogous to the movements of beings toward complete enlightenment, a sort of boiling up to enlightenment through the stages of Bodhisattva, to the 10th Bhumi stage of enlightenment of enlightened beings. Does an enlightened mind burst fire with enlightened activity, or is the chaos between periods of quiet a microversion of a bardo journey? Do electrons journey in the bardo? It is always interesting to suppose in our search for truth that there might be an order that is inherent in the physical and spiritual worlds, that things really are of a piece. For the rhythm of the human heartbeat reflects a perfect proportion of the time it takes the earth to circle the sun. According to Min anyway, a few years before Mandelbrot was born, two French mathematicians, let's see here. Here we have a little bit about Mandelbrot. A few years before Mandelbrot was born, two French mathematicians, Gaston Julia and Pierre Fortoux, sought to map out the complex plane by undertaking a series of iterations, mathematical processes of progressive change. During the turmoil and tragedy of World War I, the Frenchmen found in their analysis the deep ordering of attractors, naturally rising points in the complex plane that attracted surrounding points to them, and conversely, other points that acted as repellers. The boundaries around the catchment areas of the attractors were made of repelling points and proved to be extremely complicated. So much that decades before the advent of computers enabled the revelation of the exquisite details, the two men never saw the incredible beautiful fractal forms that their attractors and repellers exhibit, and that are now known as Julia sets. What they discovered, though, would be instrumental for Mandelbrot's later work and how such fractal attractors apply to apparently chaotic and complex systems. Another crucial contributor to Mandelbrot's discoveries was American mathematical physicist Michel Feigenbaum, who also investigated the nature of iterations. He was especially interested in understanding how, when, variables within systems pass certain thresholds, the entire system undergoes bifurcation or branching. The more sensitive a system is to a certain variable increases its responses and leads to further bifurcation, with each branch itself splitting into a further two. Unless halted in some way, the rate of the continued doubling of the splitting up approaches even closer to a single point, known as the Feigenbaum point, where the system enters a chaotic state. Vitally, though, even within the chaos are areas of order that can become fractal seeds of emergent new stability. Feigenbaum found that the ratios between successive bifurcations converge to a specific number, 4.66920616, regardless of whatever systems are studied. Like pi, another never-ending and never-repeating irrational number, Feigenbaum's number is a truly universal constant of our universe. His understanding, however, emerged from studies concerning and solely measuring real numbers. It was only when Mandelbrot used the power of computer analysis to combine the understanding of attractors and Julia sets with the extension of Feigenbaum's insight to the complex plane that a vastly greater and even more profound picture emerged. Mandelbrot was aware that Julian Fatou had discovered two types of fractal Julia sets. One is made up of completely disconnected groups and the other of completely connected ones. And he wanted to understand the deeper pattern that caused the two types. He did so by iterating the simplest form of transformation that generates further complex numbers and effectively map the complex plane onto itself. In 1980, he decided to map the mapping by coloring in points from which arose connected Julia sets and leaving blank the points from which disconnected sets emerged. This identified all connected and disconnected Julia sets in what came to be a single larger set, now famous and named after Mandelbrot. For what came out of the computer was as utterly unexpected as it was utterly wonderful. The inside and the outside of the geometrical Mandelbrot sets was the boundary between all connected Julia sets inside and all disconnected Julia sets outside. It's the boundary of the Mandelbrot set, though, that's truly extraordinary, and that marks the embedded Julia sets as being exactly on the cusp between connection and disconnection. It's here where the zooming in at the smaller and smaller scales reveals ever smaller and embedded Julia sets. Mandelbrot had literally discovered that the fractal harmonics of creation. What they opened the doorway to was a realization that all physical, complex and chaotic systems are based on underlying non-physical complex plane attractors and fractal patterns, and how the complicated and diverse appearance of real world arises from the intrinsic order, and how the complicated and diverse appearance of the real world arises from the intrinsic order and instructions of simple rules, principles, relationships and geometrical patterns in a realm beyond space and time. This is when we're closest to the Wigner equation, the Wheeler-de Witt equation, sorry. These harmonics of creation, and whose attributes are those of the cosmic hologram, underpin the entirety of our universe at all scales of its existence. It's by understanding the informational content of such attractors that further insight into the premise that while probabilistic, no phenomenon is ultimately random, is gained. Throughout the holographic processes that on a myriad of levels play throughout the whole world, individual probabilities accrue to form collective determinism. For example, the heights of individual people vary, yet they are not random but probabilistic. The biofield template of a human being holds information that results in a statistical range that goes from the scale of a newborn baby to the height of the tallest person in the world. Collectively, the range is deterministic. So if the heights of everyone living were plotted on a graph against the frequency, the number of people at that height, the overall distribution would be in the shape of a bell, whose peak corresponds to the overall average, as in the case for heights such as so-called Gaussian curves, describe the normal distributions of characteristics of many types of populations. Indeed, it turns out that the distribution for Gaussian curves, which arises from a family of stable fractal attractors, also embody within any population the maximum amount of informational entropy for a given average and range of variance for a specific characterized analysis. And fractal pulses and how the complicated and diverse appearance of the real world arises from the intrinsic order and instruction of simple rules. Another thing to be looking at here is the Fibonacci series of integers. Another example is the Fibonacci series of integers, and I need to explain a little bit here. You see, the Mandelbrot sets includes everything that is inside the set, also depicts what is on the outside. Do you realize how much more information that makes possible? And this is how this is transferred to the height of the population, the median income. When we take the inside and the outside together, we can also see what the inside depicts also indirectly depicts the outside. The abnormalities depicts the normality and vice versa. The Fibonacci series of integers, all series as the Lucas series, which begins with 2, 1, 3, 4, and so on, whose progressive integers like Fibonacci's are added to one before, and where each is then divided by its predecessor, converge to phi, regardless of the two numbers. A number of geometers felt this revealing somehow something profound yet elusive about the deeper structure of reality. In recent years, the mathematics of Fibonacci and Lucas functions has been combined with the so-called hyperbolic geometry that describes flat spacetime, named after Minkowski, who not only pioneered its understanding as we've seen, but was also Einstein's teacher. Such geometry, which enables events and their causality in spacetime to be tracked, is the one which his specific theory is the one which his special theory of relativity is most often formulated, while the real-world significance of Fibonacci and Lucas hyperbolic functions, I know another snappy name, is an open question. I suspect it will be found to have important connections with the beginning and ongoing expansion of our universe. Watch the space-time influences shape, size, and stickiness. The two key characteristics of manifestly very different phenomena that have probably surprised researchers the most are, first, the very widespread commonality of patterns and relationships underlying their varied appearances, and second, how apparently complicated real-world structures and systems can be effectively computer modeled using simple rules. Both these unexpected results began to be uncovered in the late 1960s. By 1970, an insight of what might be going on was reported by physicist Leo Kadanoff through studying the behavior of critical points at the edges of order and chaos for phase transitions, such as when water vapor either cools down or is put under increased pressure when it condenses to form liquid water. In the late 1980s, the more groundbreaking work was carried out by physicist Per Bach and his colleague Chao Tang and Kurt Wiesenfeld at the Brookhaven National Laboratory of Long Island, New York, who decided to play with piles of sand in increasing the height of the pile by 1 grain of sand at a time. At some point, the addition of a single extra grain, to mix metaphors, the straw that broke the camel's back, caused the pile to collapse. At this critical point, they measured how the collapse could be small, with only a few grains falling down the slope, or result in an avalanche. Rebuilding the pile again and again, they continued to plot other small and large collapses. What Kadanoff, Bach's team, and further researchers showed using other materials and studying both real systems and by running computer simulations. Using other materials and studying both real systems and by running computer simulations was that the behavior of ongoing dynamics between order and disorder in such systems is in principle exactly the same, completely regardless of their apparent diversity. It's due only to how easy or difficult it is for an informational ordering or disordering influence at one point in the system to bring order or disorder to another nearby. And it's only the basic shape and physical size of the elements of the systems that matter and that affect the type and scale of this influence, nothing else. In other words, shape and size, their consequential stickiness are the sole factors that needs to be considered to fundamentally understand and model the system. What this universality also tells us is that any circumstances that embody the same simple criteria will behave in a similar fashion, regardless of their apparent dissimilarity. Such varied systems belong to a so-called universal class, and when the characteristics of one member of the class are understood, all other members of the same class can be treated in the same way. And because of the state of the system only appears to depend on the basic factors of shape, size and stickiness to affect in model its behavior, one can simply exclude all other details, however complicated they make up its appearance. You see here now, when it comes to the statistics of heights, what the shapes in the geometry of trying to show the different variations in height, that will form a geometry. And the shape of that geometry will be the thing that we can read off. This is inherent already in the discovery from early on with Quo's theory, with Benoit Mandelbrot, but that was later clarified as to be exactly so. Remember the Feigenbaum constant. It goes slash through all the scale and what we usually consider to be completely different things. This differentiality is now being pointed to not being of complete truth. It can actually have covariance, similarity in structure, and that can decide how we regard those systems. So they're not as closed off as we generally think. We generally think all those things to be completely isolated and having nothing to do with each other. Complexity, the scale, invariance and harmonic order of fractal patterns, power laws, and the spread of systematic influences are also aspects of the future of so-called complex systems, such as those we already looked at, including earthquakes and landscape formation. Here we'll bring these and other features together to describe the general behavior of such systems and how they can be understood in informational terms. And the next two chapters will explore them more specifically, first in terms of evolutionary biology and ecology, then in socioeconomic systems that we experience in our everyday lives. To begin with, their complexity generally develops step by step through non-linear processes where a tiny event can trigger either a small dislocation or a major upheaval or vice versa, and which takes them far beyond equilibrium to a critical state, where they exist at the edge between order and chaos. The spread of such non-linear influences of order and disorder is crucial to the behavior. Not only, however, does such influences take time to effect, in many instances they are also not one-way processes. Instead, they can involve both positive and negative feedback loops that either augment or damp down the initiating influence. The study of complexity emerged from early research in chaotic systems, whose outcomes are the result of relatively few non-linear interactions, and whose conduct is less governed by the past until they pass through the threshold point, such as specific temperature or a level of turbulence, when they tip into chaos. Complex systems, though, embody numerous interactions, and for them history definitely matters. All events in their past accumulate to form the present, and all current events irreversibly contribute to the future. In contrast to chaos, studying complexity really is about trying to understand how simple behavioral patterns can somehow self-organize to lead to an enormous number of often complicated and dynamic relationships that, despite being at the critical edge of chaos, are nonetheless able to exist on sustainable basis. They can do this as they're informationally underpinned by a fractal attractor within whose parameters a robust variability of factors can continue to maintain the system, albeit within limits. One such complex system is the weather, whose underlying attractor is named after the meteorologist Edward Lorenz, and whose mapping in the complex plane reveals the beautifully symbolic shape of a butterfly. While Lorenz's first computer model depicted chaotic behavior, in his recognizing the longer-term stability of weather patterns, he decided to look again for complexity. In doing so, he actually simplified his math, ending up with three short nonlinear equations from which a complex, dynamic, yet inherently robust system emerges. The specific state of the system at any one time can be anywhere within the limits of the attractor, and the motion of the system never exactly repeats itself. That's led him to coin the term butterfly effect in his seminal 1972 paper titled Predictability: Does the Flap of a Butterfly Wings in Brazil Set Off a Tornado in Texas? Recognizing that very small differences in initial conditions can produce very different outcomes. This also means that despite the enormously more powerful processing power of computers since the 1970s, the weather still can't be forecast for more than a few days ahead. You might be asking that if the weather can't be forecast, how can climate change be anticipated? The reason is that while precise short-term weather behaviors are unpredictable owing to the sensitivity of future outcomes to specific initial conditions, by statistically averaging these out, much more foreseeable longer-term trends can be discerned. There is an elephant in the room with such long-term expectations, however, and as we will soon see, it's incompatible with the survival of the butterfly. And let me also mention here, many people say that quantum physics disappear in the predictability of the long term and the high quantity. But look after which is the first thing. It's the quantum phenomena. You can compare the quantum phenomena with the butterfly effect. It is actually the thing that decides. And you can always erase that feature by having huge statistics. Before we do, we need to ask a key question. How do complex systems evolve to enable the robust level of sustainability they embody? Early insights were again proven by Buck, Tang and Wiesenfeld in their work on sand piles in the late 1980s. Well, I mentioned that before. What astonished Back and his colleagues was that the sand piles reached this point without any apparent external regulation, and so they described the system as having developed a property of self-organized critically. In their breakthrough paper of 1987, they also state the emergence of such critically wasn't dependent on the exact details of the system and allowed flexibility and variability in reaching its critical state. While providing significant insight into such complex behavior and the characteristics of the processes that bring them about, they, and indeed many others, researchers, who continue striving to understand such systems, are still trying to determine what it is that organizing about them, how they do it, and what's happening in them that's different from other non-complex systems. To get closer to answer these fundamental questions, we need to understand how energy and entropy, and most importantly, information flow through these structures. Pioneering works by physicist Edwin James in the 60s, physical chemist Ilya Prigogine in the 70s, and many other scientists have contributed to the following general insights that nonetheless are still being debated as active research continues. Key attributes of such complexities include, first, that such systems are always dynamic and open to slow and steady flows of energy through them, and while far from equilibrium, are able to sustain energetic stability so can exist in a semi-steady state. Second, causality prevails throughout such system, and history matters, as past events are inherent drivers of the future behavior. In other words, such systems are reproducible and can evolve. Third, they embody long-range interaction that optimize their interconnectivity. Fourth, the selection principle that seems to apply to their developmental states is that, subject to any externally imposed constraints, the flow of information entropy is maximized. Very important. Thereafter, as semi-stable organizations, informational flow gradually decreases to minimum ultimately resulting in an unchanging state, stagnation, or death. I would say that's the same as the death by dissolution mentioned by Heraclitus. Finally, such systems optimize the distribution of information expressed as energy, with a distributed intelligence, then enabling them to be both robust and capable of repairing extensive damage to themselves. Wow! Breakdown or breakthrough. Even when such systems are robust, however, circumstances can arise where the ability to respond and adapt is severely compromised, and they're forced to undergo what are called critical transitions. Even though they are sustainable, nonetheless self-organized complex systems exist in critical states, on the edge between order and the turbulence of chaos, between the ventral and the dorsal surfaces. Think that. Yet their intrinsic attributes enables them to remain stable within the limits of their fractal attractors, often for a considerable periods of time. As more and more evidence mounts, it's becoming ever clearer, though, that many, and indeed perhaps all such systems, have critical thresholds, one or more tipping points beyond which the system inevitably and often suddenly transforms from one state into another. With such a system's innate non-linearity of cause and effects, trying to predict such critical transitions is extremely difficult. The more so because its organization may show little significant change before the tipping point is reached, but after which, like Tom chasing Jerry off a cliff, there is no going back. However, given such complex structures include everything from financial markets, social structures to ecosystem systems and our global climate, identifying stresses and early warning signals prior to tipping point breakdowns is extremely important to our collective well-being. For this, to take an urgent example, is where the elephant of possible unstoppable and catastrophic climate change charges into the room, wreaking havoc and potentially crushing the butterfly. In computer models and experiments with the simplest of complex systems, there do, however, appear to be a few features of behavior that characterize the approach of systemic breakdown. The first is a phenomenon known as critical slowing down, or CSD, during which the system recovers progressively slower from small perturbations, rather like someone with a compromised immune system, finding it harder and harder to recover from minor health issues. As for a person's health, such CSD behavior tends to begin quite far away from what eventually is the tipping point, after which a critical shift in the system is inevitable. Its continuation, though, leads to changes that constitute a second type of process that is called autocorrelation. This relates to the presence of repeating patterns over time of fluctuations within the system's behavior, and when a tipping point is approaching, the level of pattern repetition diverges from the norm. The third sign, which arises from instability at limits of what the existing fractal attractor of the system can handle, is that it becomes more variable with progressively skewed changeability in its behavior. Systems that are sufficiently destabilized may also exhibit what's known as flickering, where the system wobbles between alternative states before undergoing a sudden transition to one or other of them. Giving their importance, a great deal of research is being focused on identifying and finding ways to measure these early warning signals, where there are enormous difficulties giving their levels of subtlety and uncertainty, and the challenges of studying real-world examples. Political dysfunction, though, concerning public debate and policy regarding climate change impairs not only effective global action in responding to currently perceived longer-term threats, but leaves us helpless in the face of such potential catastrophe. Well, that was rather interesting and rather long. I think this was the most intense work day ever. I say thank you very much for your patience and have a very nice evening. Bye bye.